everybody, it's MoNaCo.
And Milks.
We are recording our first video, video 1 in our new unit.
Yep. Unit 6, Physical Behavior of Matter.
Okay, you'll notice all the videos are numbered now, so you're in video 1. If you're watching and paying attention, that's where you're at.
There you go.
Hit it!
All right, page 4 and 5. As always, let's start off with our key vocabulary so we know what we're talking about.
Yep. And this unit, we're going to be using some similar words and some brand new ones. The similar words, we're going to put a new definition on.
Yeah.
And the brand new ones are very specific to this unit, and you just got to get a hang of them.
Right. I would think that instinctually we know a lot about these topics, but we need to flesh them out. We need to get a well-rounded, theory on these things. So first, temperature.
It's a measure of the average kinetic energy of a sample of matter.
Okay. Very good.
What does that mean?
Well, we're going to learn that kinetic energy is the energy of motion.
And so this is the average motion of the atoms in a sample.
Sure.
Measure
Which
it with a
is
thermometer.
heat.
It's indirectly, it's related to heat, yeah.
Yeah.
Right. So here we go, heat transfer.
Always, always, always from hot to cold.
Right. Cold doesn't go. Heat leaves.
Right.
Cold doesn't creep in when you open the window.
No,
the heat leaves,
yes,
and you feel it leaving as cold.
Sure, and we've got to think of things as a system,
right,
and conceptualize. When you grab something that's cold, you're not feeling its cold coming into you. You're feeling your heat leave into it.
Right. So there's a matter of perception in this hot-cold thing. We'll get into that in detail in just a moment. Kinetic energy. This is the energy of motion. I mean, kinetic is derived from Greek's terminology for motion, moving.
Yes.
So atoms are in constant motion, and they have kinetic energy, which we measure as temperature.
Right. The more I heat them up,
the quicker they move.
The more energy they have.
Potential energy.
Now that is it. In physics terms, it's the energy of position.
Mm-hmm.
Okay, we're going to try and relate that into chemistry. For this unit, it's really going to be phase change.
Energy of a phase change.
Yeah, because I'm still heating it up.
Right.
But now there's going to be spots where our temperature doesn't increase.
Right.
And all that energy is going into changing the phase, and that would be the potential energy.
Like changing the position of the atoms in relation to each other from a solid to a liquid to a gas. You know, they principally move differently, so that's what potential energy comes into this unit.
There you go.
This is new.
Yes.
Kinetic molecular theory.
Yeah. 5 postulates, or what would you call those?
Rules.
Rules. Great.
Facts.
Yep. Used to explain how gases behave.
Right. So it's like the 5 bullet points you got to knows about how a gas goes.
Yeah, and they get to be fairly predictable.
Yeah.
Right.
And you might already know a couple of them, to be honest.
I think you instinctually you do. Yes.
Next one, new. Absolute zero.
Yes.
This is a really cool.
I wonder if they've heard about this before.
I hope so, because it's new, but not really that weird. This is a theoretical temperature where all motion stops. So it's like the joining point of temperature, kinetic energy, and heat. It's how the point, like where theoretically none of it happens anymore. Atoms done stopped moving. There's no heat involved. There's no kinetic energy involved. It hasn't actually happened yet.
No.
As a human race, we haven't gotten there.
No, we've gotten very, very close, within
billionths of a degree.
Right.
But guess what? Atoms are still trucking along, doing their own weird new things at that point. So we're not getting further than absolute zero as it relates to temperature, and you'll see that in a later video.
Yeah. Good.
What else we got? Oh, you know this one.
Normal boiling point. Yeah. So this is the temperature at which liquid boils, any liquid, at specifically 1 atmosphere, and that
pressure.
Right, and we would consider that 1 atmosphere normal pressure.
Right.
So therefore, we get the normal boiling point.
So like, absolute zero is the meeting point of temperature, motion, of kinetic motion, and heat. Normal boiling point is the merging and the meeting point of pressure and temperature.
Yeah, and vapor pressure.
And vaporization. So like these 3 concepts kind of go into when we teach about normal boiling point.
Yep.
Which is cool stuff. You'll
Just
see some neat demos there.
Right, and that 1 atmosphere gives us that basis of comparison, a normal pressure.
Cooling curves and heating curves are graphical representations of kinetic and potential energy as a substance is cooled or heated. We like to track things with graphs. You're going to see and get to know these and what parts are important. Big major part of the unit is knowing those curves, special spots on them where potential and kinetic energy are changing.
Right, and I'll just throw it in there that we'll see that the kinetic energy, when we see that part changing, the temperature will be changing.
Because temperature is a measurement of the kinetic energy.
There you go.
So.
And then when it flattens out, but I'm still heating, that's where, wow, dude, I'm adding heat, but the temperature isn't changing. What's going on?
The position of the atoms must be changing.
There you go, and that'd be our potential energy or our phase change. Right. We'll see that.
So those two things are very important. Evaporation. Everybody knows evaporation. We're going to put a little twist on it. This is where the surface of a liquid, like that monomolecular surface of the liquid, changes into the gas phase. It explains why, in conjunction with vapor pressure and stuff, why a puddle of water at room temperature can evaporate.
Right.
Because we all know that water don't evaporate until 100 degrees Celsius.
Well,
How come that
right.
puddle of
It
water
doesn't-
went away?
So there's the difference between like vaporize and evaporate. I always like to think evaporate will happen due to a gradient difference. If it's really dry
Slowly
outside,
changing.
it'll evaporate faster if it's dry. And if I add heat to the liquid, it will evaporate faster.
But it always comes down to that surface of the liquid and changing from the liquid to the gas phase.
Specifically.
Heat of fusion.
So this is the amount of heat needed to completely melt a solid with no change in temperature.
Right, and there's a cool unit for it, or an abbreviation I think we forgot to put, capital H, lowercase f, heat of fusion. Okay, so put that in there on your notes too. That's how we refer to it later.
Okay. And very much the same, heat of vaporization.
That's the amount of heat of completely evaporated gas with no change in temperature. So the amount of energy it takes to vaporize something, capital H, subscript V. Okay? Heat of vaporization. These are different quantities for different samples of matter. The heat of reaction, important stuff.
Yep. This is specifically, again, the delta H of the products minus the delta H of the reactants. This is going to basically show us the overall change in heat as the result of a
chemical reaction.
Was heat given off or was heat put in?
This is for chemical reactions, not physical changes, chemical changes.
Yep.
And this is related to a special reference table. That's why we're teaching it here.
Sure. And we'll come back again to that exo-endothermic that we've learned.
Right, good.
So that's part of it.
We're going to rate delta H to exo and endo. Heat moving in and out. Cool. Melting point, freezing point. The reason I put it in here is because it's a great misconception. Mr. Milks, what temperature does water melt at?
Water melts at 0 degrees Celsius.
Okay, Mr. Milks, what temperature does water freeze at?
Again, 0 degrees Celsius.
Wait a minute, they're the same temperature. How could two things be happening?
Well, now the difference is direction of heat flow.
Right, so you mean that hot to cold, cold to hot thing
That's
is
right.
going to matter?
It is going to matter. So if I'm cooling something, I will go from liquid to solid, which is freezing.
Because the temperature, the motion of the particles is going to drop.
Right, stop.
And
Right.
move, slow
Move
down.
less. And the opposite's true.
Right.
If I melt something, I must be heating it up.
Mhm.
And it's going to happen at the same time.
Right, so you got to pay attention to the direction that the heat's flowing above all when we're
Sure.
dealing with this stuff later.
Sure.
So vapor pressure is the pressure created at the surface of the liquid as the molecules of the liquid push up on the atmosphere. It's the reason why a puddle of liquid water can evaporate even if it's in a room that's not 100 degrees Celsius.
Yeah.
The surface of that liquid is special things going on. Those atoms are trying to push back on the atmosphere and jump up into the gas
This
phase.
vapor pressure piece is really the scientific part of the evaporation.
And also connected to boiling point, temperature, and pressure.
Absolutely.
So-
Which, when we wait till we redefine those.
Yeah, cool stuff.
Calorimetry is just the measure of heat.
Right.
We've heard of calories before.
Mm-hmm.
Like how many calories are in those potato chips,
For sure.
right? And what they really do is they burn them.
Right, and they burn them, and they release all the heat that was bound up in those chemical bonds.
Yep.
And that heat gets transferred from a hot flame to a cold bucket of water.
And we measure the temperature change.
You measure the change in temperature of the water and do some calculations that deal with specific heat capacity, heat of fusion, vaporization, and stuff, and say, well, the water changed by a certain degrees Celsius. Duh, we burnt something underneath it. That must mean that this much heat was absorbed, and that heat is measured in joules or calories, and that's exactly how they figure out a Snickers bar is not good for you.
right.
It's not
There's
good.
way too many calories.
Way
right?
too many empty calories.
Particle diagram, I think we probably all know what this is. This is just going to be a quick diagram to show me the arrangement of particles or atoms. Helps me differentiate between solid, liquids, gas.
And I just realized this is essentially showing you the potential energy of the molecules at any given moment. If it's a solid, they're stacked up next to each other. That's the energy
Yeah,
of
so
position.
they don't have a lot of room to move.
Right, etc. So a particle diagram is really connected back to potential energy
gives me
and
a little
kinetic
picture.
energy in this unit, for sure. So hopefully the video, audio. Oh, wow, we got more. I thought that was it. Gosh. Ideal gas
Oh,
behavior.
this is a good one. This is a good one.
This is when a gas is at high temperature and low pressure and will obey the kinetic theory most closely. So there's 5 rules. We showed you at the beginning there. An ideal gas is when the gas is behaving most like it's supposed to.
Sure.
Under that theory.
Sure. We use the word ideal because then at that point it becomes very predictable.
And we chemists and scientists love to make predictable models.
Sure, especially when
And
we do all
use
this math. I want to be able to know exactly what my volumes are.
And this is where the math is going to show up.
Sure.
Combined gas law.
We're going to learn about these 3 separate laws. There's the Charles law, the Boyle's law, and the Guy-Lussac's law. We're actually going to do a lab that has to do with all 3 of these laws individually.
Yep.
And when we put them all together, we call that the combined gas law.
Because it combines 3 different gas laws. Right.
There you go. And then here's the one that's been
Good
plaguing us
old
all
STP.
year.
Everybody doesn't know what this is, and my gosh, you better know it after this unit.
Seriously.
It's reference table A. I mean,
True.
the first one.
Yep. There it is, right there.
And the temperature of 0 degrees Celsius and pressure of 1 atmosphere.
Exactly.
This allows chemists, scientists to compare sets of conditions across countries, continents, planets even.
Right.
Well, what was the temperature? What was the pressure? It was this. Well, in relation to that, then this must have happened. It's a basis for comparison.
Right. And
You
it's
gotta
one of
set
those
the
things
bar.
where we want, when you want to make comparisons with, this changes this, you want to only to change one variable at a time.
Right.
So these are some of those variables we need to keep constant across the board.
2 other things I want to add here. This is at the same temperature. 273 Kelvin is 0 degrees Celsius.
Next.
This is definitely in our video, but it's also on our reference table. And the pressure, atmosphere, is also listed as kilopascals. They're different units measuring the same
Magnitude.
thing, same magnitude. The size of the pressure or temperature is involved there. So there we go. You got to know your vocab.
Yes.
I mean,
Make sure you know all these things, guys. These words are going to come up time and time and time again, and we can't have more misconceptions than not.
Please come down.